This is Indira, Assistant Professor of Institute of Aeronautical Engineering, and we are going to start with linear algebra in calculus, which is a mathematics topic of engineering mathematics. In this linear algebra in calculus, we have the following topics. That is the 5 topics, that is theory of matrices, linear transformations, functions of several variables, higher order differential equations, and partial differential equations and its applications. In this, the first 2 units, the first 2 modules are based on matrices, and the third module we have maxima and minima, that is the finding out the maximum and minimum value of functions of several variables. And the 4th module we have higher order differential equations, ordinary differential equations, and the 5th module we have partial differential equations. So going to the first module, that is theory of matrices, we have the properties of real and complex matrices, the properties of real and complex matrices, the 3 important properties of real matrix, that is symmetric, skew-symmetric, and orthogonal matrices are discussed. Similarly, we are going to have the 3 important topics, that is Hermitian, skew-Hermitian, and unitary matrices and in complex matrices. And the next topic we have is elementary row and column operations and how to do the elementary row and column operations. And next we are going to find out the rank by 2 important methods, that is echelon form and normal form. Echelon form and normal form. And the last, and we are going to have, that is the finding out the inverse by Gauss-Jordan method. Almost we are very familiar of finding out the inverse by elementary row and column operations in the elementary classes. Now we are going to find out the inverse of a given matrix by using Gauss-Jordan method. So these are the topics which are there in module 1. So we are going to start with the theory of matrices today, and this engineering mathematics, that is linear algebra and calculus, the course focuses more on advanced engineering mathematics topics, and which provide with the relevant mathematical tools which are required in the analysis of problems in engineering and scientific professions. The course includes the types of matrix and its applications, and maxima and minima of functions of several variables, and solutions of higher order differential equations and the partial differential equations with its applications. The mathematical skill derived from these courses forms a necessary base to analytic and design concepts countered in the problem. Okay, so this we are going to start with the very first module, that is theory of matrices. In theory of matrices, the first thing that we have to learn is the definition of the matrix. The matrix is nothing but the arrangement of or array of elements in rectangular rows and columns. If you arrange the elements in rectangular rows and columns, the counting and the operations becomes very easy. And in general, this matrix is it is represented by A, that is square bracket A I of M cross N, where M and N, where I is a row, we are representing row, and J is nothing but the column. And I, it lies between 1 to M, and J, it lies between 1 to M. That means that M is nothing but the number of the row that we are representing, and N is nothing but the number of the column that we are representing. So this is an example for M into N matrix, that is AI, A11, A12, so on up till A1N. And similarly, the last row is AM1, AM2, so on up till AMN. Okay, M into N. And A11, A22, A33, they are all nothing but the diagonal elements. So this is the general notation of matrices. Now, Going to the properties of going to the real matrix. When a matrix is said to be real matrix, if each and every element of a given matrix are real numbers, that means we don't have any complex number in the given matrix, then you call it as a real matrix. If any one of the element is a complex number, then you call that matrix as a complex matrices, and that we call it as a complex matrix. There is no rule that all the elements of the given matrix should be a complex number. If at least one of the number is complex, then it is denoted by complex number, and if all the elements are real numbers, then you call it as a real matrices. Both the real and complex matrices plays very important role in engineering mathematics, and most oftenly this matrices is used to find out the solutions for the linear equations, all linear equations at a time. Okay, suppose if you want to find out the solutions of the linear equations, take an n number of linear equations at a time, then this, by using this matrix method, it's very easy for you to calculate, and matrix plays very important role in all fields of engineering mathematics. Now, so the very we are not going to discuss about the very elementary properties of elementary matrices, that is diagonal matrix, null matrix, all that we have already done in the previous classes. So we'll start with the properties of the real and complex matrix. To understand the properties of real and complex matrix, we need to understand what is a conjugate transpose of the matrix, where you all know what is a transpose of the matrix and what is a conjugate of an element. We don't call this conjugate of a matrix, we call it as a conjugate element. So in a complex numbers, suppose you have x plus iy, suppose you have x plus iy, the conjugate of it is represented by x plus iy whole bar, which is equal to x minus iy, which is equal to x minus iy. So what I mean to say that the conjugate is an operation which is done on the elements, and transpose is an operation that is done on the matrices, which is done on the matrix. That means that a matrix transpose is nothing but is obtained by interchanging its rows in columns, right? Now, the combination of this transpose and the conjugate is nothing but the conjugate transpose of the given matrix. So before that, let me understand what are the conjugate of the matrix. The matrix obtained by any given matrix A by replacing its elements by conjugate complex numbers is called as conjugate of A, and it is denoted by A bar. The familiar properties of conjugate of the matrix is A bar whole bar is equal to A. What I mean to say that, suppose if I have taken x plus iy whole bar, then which is equal to x minus iy, if you do once again the conjugate of this, we are going to obtain x plus iy, which is nothing but the same matrix. So A bar is nothing, A bar whole bar is always equal to the matrix itself, right? And the sum, if suppose if A and B are the two different matrices, the conjugate of A plus B is nothing but the conjugate of individual matrices A bar and B bar. And similarly, the scalar multiple of the matrix A, if you do the conjugate of that, then this conjugate operation will affect the K if and only if K is a real number, right? That means that if K is a real number, then you can say that K A whole bar is equal to K into A bar. If K is an imaginary number, if K is an imaginary number, then K A whole bar is equal to K bar into A bar. Suppose if I have an I into A is a matrix, then I A whole bar is nothing but I bar into A bar, where I bar is nothing but 1 by I. So into A bar. Is it clear? Okay. So in this way, you can say that we can say that K into A whole bar is equal to K bar into A bar. Similarly, if suppose A and B are the two different matrices, then the conjugate or the product of the two different matrices is equal to the product of individual conjugates, that is A bar into B bar. So that is how we can understand the conjugates of the given matrix. Now if the next is we'll impose one more operation on the conjugate matrix, that is transpose of the given matrix. Okay, that means what is this? It is always represented by theta, where theta is nothing but in the matrix A bar transpose, A bar transpose, or A transpose whole bar, A transpose whole bar, one at the same. And here the conjugate and the transpose, or transpose and the conjugate, both are commutative with each other. That means that any operation, if you do conjugate first, then transpose, or transpose first and then the conjugate, both are one at the same, right? Both are one at the same. Here I have given one example, 5, 0, that is I have taken 2 into 3 example. Let us see what you are going to get if you do the transpose conjugate of this matrix, right? 5, 0, 3 minus I, 1 plus I, minus 2I, 4 minus I. Okay, what is A transpose? A transpose is equal to interchange the rows and columns, 5, 0, 3 minus I, 1 plus I, and minus 2I and 4 minus I. This is the transpose of the matrix, right? Okay. Now what is it? A transpose whole bar, which is equal to you do the conjugate of each and every complex number. 5 and 0 are the real numbers, so you don't have any conjugate of that. And the next number is nothing but 3 minus I, whose conjugate is 3 plus I, and 1 plus I, which conjugate is 1 minus I, that is, and that 2I and 4 plus I. So this is nothing but the value for A to the power of theta, that is nothing but the conjugate transpose, right? Okay, now the next important properties of real matrices are symmetric and skew-symmetric matrices. When a matrix is said to be symmetric and when a matrix is said to be skew-symmetric, and these two are the special properties which are given on the square matrices, okay, not on the rectangular matrix. Suppose if I have A is any square matrix, if suppose A transpose is equal to A, then you call it as a symmetric matrix. And if A transpose is equal to minus A, then you call it as a skew-symmetric matrix. Okay, now here I have taken an example for the symmetric matrix A, H, G, H, B, F and G, F, C. You can see that the transpose of A transpose is again equal to A. So this is the best example for the symmetric matrices. Similarly, in the skew-symmetric matrix, I have quoted another example, 0, A, row wise I am talking, minus B, minus A, 0, C, B minus C, 0. You can observe that the diagonal elements here are always 0, because this operation A transpose becomes minus A if and only if, for the real matrix I am speaking about, for the real matrix A transpose is equal to minus A, then diagonal elements must and should be 0. Otherwise, if you take any non-zero element, this property may not be satisfied. So if you observe that for skew-symmetric matrices, the diagonal elements are always zeros. So these are the important properties on real matrices. Okay, real matrix. Now the same as we have talked about the symmetric and skew-symmetric matrix, another important the properties, the similar type of properties we can talk on complex matrices also, that is Hermitian and skew-Hermitian matrix. So let us understand when an element when a matrix is said to be Hermitian and when a matrix is said to be skew-Hermitian matrices. You all know, suppose A is any square matrix, if I consider A as any square matrix, A to the power of theta, if A to the power of theta is equal to A, then we call it as a Hermitian matrix. That means that the conjugate transpose of the given matrix is again a matrix again, then you can call those that type of matrix as Hermitian matrix. Okay, if suppose a conjugate matrix of the given matrix is equal to minus A, then you call it as a skew-Hermitian matrix. You call it as a skew-Hermitian matrix. Hermitian matrix, right? So here I have given one example, that is 1 plus I, column wise I am reading 1 plus I, 2 1 minus I, 3 minus I, 2 I, 0 is the best example for Hermitian matrix. Okay, you can check here, okay, whether A bar transpose we are going to give the A again, right? Okay, now you can observe that the diagonal elements of this Hermitian matrix are always real numbers. As we have talked about the skew-symmetric matrix, the diagonal elements are zeros. So here also we have the special character on the Hermitian matrix, that is the diagonal elements are all real numbers, right? Okay, so similarly, if you go talk, that is the Hermitian matrix can also be defined as a square matrix A, in which the transpose conjugate of A is equal to A, that is A bar transpose is equal to A, or A to the power of theta is equal to A. Both are one and the same. So similarly, if you talk about the skew-Hermitian matrices, now we have both types of definitions are there with me. That means elementary wise definition of skew-Hermitian matrix. Suppose Aij is any element of a given matrix. If Aij is equal to Aji whole bar, then you can call such a type of square matrix as a skew-Hermitian matrix, right? That means that A to the power of theta is equal to minus A, and this is possible if and only if the diagonal elements of the given matrix are either purely imaginary or zero. So we can conclude that the diagonal elements of the skew-Hermitian matrix are either imaginary, purely imaginary, or they may be zeros. So here I have a good example. I minus 1 minus I minus 2 1 minus I 3 I 2 I 0 is one of the example for the skew-Hermitian matrix. A skew-Hermitian matrix can also be defined as a square matrix A, in which A bar transpose is equal to A or A transpose whole bar. Both are one and the same. Now, next property that we can talk on is nothing but the on real numbers. That is nothing but that means on real matrices, that is orthogonal matrix, right? A square matrix capital A is said to be orthogonal if A transpose into A is equal to A into A transpose is equal to the identity element. It's one of the property which is mentioned on the square matrices, not on the rectangular matrices, right? If a capital A is a square matrix and you do the transpose for that, multiply each other, you are going to get the identity matrix. If this property is satisfied, then we can call such a type of matrix as orthogonal matrix, and this matrix plays very important prominent role in matrices. Okay, and similar type of property is there on complex matrices, that is unitary matrix, that there we call it as a to the power of theta into A is equal to A into A to the power of theta. If this is equal to identity matrix, then you can call it as a unitary matrix. Okay, because here the elements we are taking is as a complex numbers, here we are taking the elements as a real numbers, and we call this as a real as a orthogonal matrix. Orthogonal matrix, right? And here I have quoted a good example that I've taken a 2 into 2 matrix. Show that capital A is equal to cos theta sin theta minus sin theta cos theta is orthogonal. Okay, now you do A transpose is equal to cos theta minus sin theta cos theta, right? Okay, now what is A into A transpose? Multiply these two, A into A transpose, that is cos theta, right, sin theta, right, minus sine theta and cos theta into the another matrix, that is that matrix that we have got here, that is cos theta minus sine theta and cos theta. We are going to get as, if you multiply these two, we are going to get it as cos square theta plus sine square theta, right? Sine square theta 0 0, cos square theta plus sine square theta. Okay, and you all know that the cos square theta plus sine square theta is always equal to 1. So 1 0 0 1, we got the identity matrix. So the A into A transpose is equal to A transpose into A is equal to I. Then you call such a type of matrix as orthogonal matrix. So that's about the properties of, here I have multiplied and showed to you cos square theta plus sine square theta, and these two gets cancelled, and even sine theta cos theta will get cancelled, and this will be equal to 1, and even this is equal to 1, and so you call it as a 1 0 0 1. So which is nothing but the 2 into 2 identity matrix. So that's about the orthogonal matrices. So we have learned the properties of real matrix, that is when a square matrix is said to be symmetric, when a square matrix is said to be skew symmetric, and the properties of complex matrix when a matrix is said to be Hermitian, and when a matrix is said to be skew Hermitian, and one more property, that is orthogonal property. So we'll continue with the same topic in the next class, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.